Hey everybody, in this video we're going to continue our study of transformations with functions, and this time we're going to look at what happens when we do things horizontally. So we saw in the previous video that when you move things, when you add 1 on the outside or subtract 3, that creates a vertical shift. So what happens when we do things on the inside? So if we take the graph of x cubed, and then we're going to explore what happens when you do x minus 1 inside parentheses quantity cube and x plus 2 inside parentheses quantity cube. So how does that alter the graph? So first of all, y equals x cubed is our parent graph, right, the main one. And this is what it looks like. And you can do it again by plotting points, but this is our standard cubic function. So that's the graph of a cubic, which sometimes I refer to it nicely as the John Travolta graph. So if you haven't seen Saturday Night Fever, so notice it has John Travolta does a very nice cubic in his dance moves. So what does f of x equal x minus 1 cubed look like? So let's explore the table of values. So if I go y equals x minus 1 cubed, and I have x and x minus 1 cubed. So what we'll start seeing is if I use my usual values, minus 2, minus 1, 0, 1, and 2, when you plug in minus 2, minus 2 minus 1 is negative 3 cubed. That's going to give us negative 27. Minus 1, minus 1, minus 1 is negative 2 cubed. So minus 2 cubed. Remember, when you cube a negative, it stays negative. So this will be minus 8. At 0, 0 minus 1 cubed will be minus 1 cubed, which is minus 1. And then at 1, 1 minus 1 is 0. So we'll get 0 there. And then 2 minus 1 cubed is 1 cubed. So we'll get 1. And so notice that as we go back up here to our John Travolta graph, in this one, we have 0, 0 is where that squiggly part happens. So where does that happen here? So essentially our 0, when x was 0, now it got moved to, when x was 0, we moved to negative 1. And so notice that our 1 here, when x is 1, now is where we get the y value of 0. So what does that mean for our graph? So let's take a look. So this is the graph that we get. So our y value of 0 is now at 1. So notice that at 1, it's right there. So 1, 0. Whereas our parent graph, at our y value of 0 was at 0. So notice that it moved over to the right 1. So essentially this creates a horizontal shift. And usually the way that I think about the horizontal shift is what makes the inside 0. So that's when x minus 1 is equal to 0. So that means when x is 1. And so that's where our horizontal shift happens. So this entire red graph, our parent graph, y equals x cubed, got shifted to the right 1. So this is y equals x minus 1 cubed. So going back to the other one, so what do you think x plus 2 cubed would look like? Where is the shift? So this is going to move to wherever x plus 2 is equal to 0. So that means that x equals minus 2. So that means that what we're going to do, so this graph, our parent graph, our John Travolta graph, is going to be shifted to the left. So this squiggly part is going to be at negative 2 instead. So let's go see what we end up with. So once we graph it, so we can see the shift here. So again, this is our parent graph, our y equals x cubed, the original one, and then any shift that you do to it. So this was our x plus 1 cube. So it's essentially our cubic moved to the right 1. And now here we have our standard cubic, but this one moved to the left by 2. So notice the squiggly part is at -2. So our y value there happens at -2, or y value of 0, sorry, happens at -2. So that's how a horizontal shift affects the graph. So now, knowing that, what if, so if we combine it, what if we put a horizontal and a vertical shift together? So say you wanted to graph y equals, say, x minus 2 cubed minus 3. Any guesses what that will look like? So think about, where is the horizontal shift? So this cubic, where does it move to horizontally? And then what does the minus 3 do? That's a vertical shift, right? Because it's outside of the x. So that's a vertical shift down. So think about what that looks like and try to graph it on your own. And now let's look at what the graph looks like. So this graph looks like this. And so, yes, it does have a vertical shift at, so what makes this 0? Or sorry, horizontal shift. So be x minus 2 is 0 when x is 2. So the squiggly part of our y equals x cubed, right? So essentially we're trying to figure out, where does our 0, 0 move? So our 0, 0 now is moved to 2, but there is also a vertical shift. So it went down 3. So our 0, 0 moved 2 units to the right and 3 units down. So this will be -3. So that's how the horizontal and vertical shift together affect the graph. And now it looks like a cubic. So one of the things that you should look at, okay, so this is a cubic, so it's going to have that squiggly, is my John Travolta. But where is that squiggly part going to be? And so I look at that is based on my horizontal shift, so the inside of the parentheses, and the vertical shift, what is outside of x. And so this will be our cubic function for this particular graph. Now the other ones we wanted to graph are, the other two functions were 2x cubed and f of x equals 1/2 x cubed. So essentially, what does that number do inside the parentheses? And you might notice that essentially if you cube this, so this will be 8x cubed and this will be 1/8 x cubed. So once you have them out, so let me write it out. So what I'm saying is, if you have, right, f of x equals, we have 2x cubed. Once you cube this out, right, this is 2 cubed and x cubed. So 2 cubed is 8 and then x cubed. So now that looks like a vertical change. So this is going to be a stretch. So it appears like it's a vertical stretch now, but horizontally, what does? And so if you think about it, a vertical stretch, what is happening horizontally? So if you, as you stretch something vertically, you're pulling it, right? So stretching it out vertically, that's making the x shrink. So a vertical stretch is the equivalent of a horizontal shrink. And so let's look at what the graph of it does. So this is what the graph looks like. So we have our parent graph, y equals x cubed, and then we have the y equals 2x quantity cubed, which is the same thing as 8x cubed. So now you can visually see it. So again, think about if this was a rope and you put your foot right at the 0, 0 and you pull it up, then you're going to be stretching. So if you think about the red graph and then you pull it, it's going to be getting it steeper, right? It's going to pull it closer. leaving the 0, 0 the same. There's no vertical shift. So vertically it's a stretch, but what's happening horizontally? So notice between, we'll go, yeah, between 0 and 2, right? This is much wider and then the blue one. So this shrunk. So we can say when there's a factor in the inside, the graph shrinks by a factor of 1/2. So this shrinks by a factor of 1/2 horizontally. And I guess to write it properly, we'll say it shrinks horizontally by a factor of 1/2. And so what about the other one? The other one that we had was f of x equals 1/2 x and then cube. So the 1/2 is on the inside, but again, you can think of it about, okay, I'm going to multiply it out. So 1/2 cube is 1/8 and then half x cubed. Now this, as we saw before, this means the graph is shrinking vertically by a factor of 8, but horizontally, that means if it's a vertical shrink, it's actually going to be stretched out horizontally. So what the graph of this looks like is this green graph. So again, notice we have our parent graph, y equals x cubed here. And then we have, this is y equals 1/2 x cubed. And again, yeah, this is 1/8 x cubed. So as a vertical shift, it's shrinking vertically, but horizontally it's being stretched. So again, focus it on the from 0 to 2. Notice how the red graph or the green graph is a lot more stretched out horizontally, but it's shrunk vertically. So it's different ways you can think of it, but essentially this provides a stretched out horizontally. So this is a horizontal stretch. By a factor of 2. So in general, say that here. In general, if you have y equals c times f of x, so we'll do the vertical first. When c is greater than 1, we stretch the graph of f of x vertically by c, by a factor of c. If when c is between 0 and 1, so a fraction smaller than 1, we shrink the graph of f of x vertically by a factor of c. So that's when you're on the outside. So if it's on the outside of your function, it's a vertical stretch or shrink. And then if your y equals f of c of x, so if c is on the inside, then things are happening horizontally. So we're going to say similar. So when c is greater than 1, we are going to shrink f of x horizontally by a factor of 1 over c. And if when 0 is less than c less than 1, so again a fraction smaller than 1, we're going to stretch the graph f of x horizontally by a factor of 1 over c. So notice that that's exactly what happened here, right? We had f of x equals 1/2 x. So we shrunk this, I said, by a factor of 2. And so 2 is the reciprocal of 1/2. 1 over 1/2 is 2. And so Oftentimes you don't see necessarily this horizontal stretch or shrinking too much because you can, if especially when it's a polynomial, when you apply the power to something like this, like when we had the 1/2 x and then cube it, you end up with a vertical stretch or vertical shrinking. So you can convert it to a vertical, and the only time that you may actually see the stretch is, say, for example, if I had something like graph y equals, say, 2x minus 1 cube plus 2. Now, right, I can't, in order to cube this, it will be really hard. Well, not really hard, but we have to work a little bit harder. It will take longer. So now I can say, okay, there is a horizontal shift. My horizontal shift will be to wherever this is 0. So 2x minus 1 is equal to 0 when x is equal to 1/2. So that's where that my John Travolta squiggly part is going to move to, right, it's at 0, 0. It's going to move to x is positive 1/2. And there's a vertical shift of 2, up 2. So this is going to move to 1/2 and then 2. So that's where the squiggly is going to move to. So something like this. And so now I can see this is going to be a c is equal to 2, right, which is greater than 1. So this is going to shrink f of x horizontally by a factor of 1/2. So it still creates a vertical stretch, but now I can't see it because I have this minus 1, so I don't have it just on the outside. So that's one way that you can interpret it. Okay.